going to be doing LeetCode Biweekly Contest 22. I'll be explaining my solutions afterwards. Oh, they added this new feature. Exactly 2 people. 2, 2, 1. In this case, I'll use a map. Can fit 2 families if they're nothing. Starts from 1. Maybe I'll just loop through all 4. This is for 1, 3, and 5. Four, 2, 4. Okay, that seems good. think it's possible to pick this. I'm missing something very obvious. I feel like it's not supposed to be that hard. Maybe any independent is, as long as they're not adjacent, maybe it's always possible. This seems to be correct, so accepted. Am I the first one? I don't think so. I took too long for that problem. I mean, this is a troll problem for sure. Like, nobody expects that to be the maximum non-adjacent subsequence sum. Anyways, I'll see if the scoreboard updates later. For now, I'll just go over my solutions. Okay, so for the first problem, you just loop through all elements of the first array and then check all elements of the second array against that element. So yeah, I loop through the first element, then I make sure that all elements in the second array have a difference greater than d. And if it's not, then OK will be set to false. And if it's false, then the answer won't update. And yeah. And for the second one, so it says that a 4-person family, you can start at either cell 2, it can start at 4, or it can start at 6. And so notice that n is very big here, and we don't want to process all of the rows. But then since the number of reserved seats is small, we only have to process the rows which have reserved seats. So I create a map here. The key of the map is the index of the row, and the value of the map is a list of the reserved seats in that row. So first I put all the reserved seats in this map. And then after that, the size of the map will tell me how many rows are not completely empty. And then we subtract that from n to find the number of rows which are completely empty. And for completely empty rows, we can place 2 families like this. So for answer for those rows is 2. And we can multiply the count by 2. And for the rows which have some reserved seats in them, first I create a Boolean array which represents if the row has been if a seat has been taken or not. And then in order to find the maximum number of families I can place, first I try to put the family starting at column 2, and I changed it to 0 indexing. So for each of the 4 seats starting from column 1, I check to see if it's reserved or not. And if none of them are reserved, that means you can put a family on that seat. So we increase the answer by 1, and then those 4 seats will become reserved. Then we do the same process for the 4 seats starting from column 3 and the 4 seats starting from column 5. And yeah. So for problem 3, this should be pretty straightforward. So first, for each of the there aren't too many elements, so we can just iterate through all of them. So if we're calculating, and then we try to calculate the power for element I. So the power starts at 0, and while the element is still greater than 1, we use the rule described above we use the step described above to change the element. And then we add 1 to the answer for each time we perform a step. And this loop will execute until the element becomes 1. So now our list stores pairs of elements and their power. So since the power is the first element of the pair, after I sort the list will be first sorted by power and then by the element, which is what we want in the problem here. So first we sort it by power in ascending order, and then by the value in ascending order. Then we just return the value, which is the second element of the pair of the kth element in the list, which is k-1 with 0 indexing. Okay, time for the interesting problem. So the first thing to notice is that you can't select 2 slices which are adjacent to each other. So for example, you can't select 5 and 6 together. And that's because once you select one of them, then for example, if you select 5, then 6 will be selected by someone else. And when you select 6, like 5 will be selected by someone else. So obviously the subsequence which you choose cannot, the subsequence that you choose cannot have any adjacent elements. So now the question is, do all subsequences which don't have adjacent elements work? Because if it's true that all sequences which don't have adjacent elements work, then we can run the standard dynamic programming solution on the sequence to find the answer. And it turns out that it is true. And we can prove that by induction. So if we have some subsequence, like if we have some array with a total of 9 elements, then we know that there are a total of 6 empty spots that we didn't choose, because we can choose 3 of them. And then at least one of between each adjacent pair of the elements that you choose, at least one of them should have a distance greater than 2. So there should be 2 empty elements between them. Wait. Wait a second, is this even... Oh yeah, okay, yeah, it works. So for example, the space from between these pair of elements, which is, we have these 4 elements. And what we can do is, we can remove our strategy for like the game will be to remove the element such that it is adjacent to at least 2 consecutive elements which are not chosen. And then we'll remove that element, and then when we remove that element, all 3 of these will be removed. And notice that since we had a space of greater than 2 here, that means after we move this, we will have a space greater than 1 on the right. So that means that it must be true that the new sequence of the new subsequence that we choose from this array where the 3 elements are deleted, none of the pairs are adjacent to each other. So yeah, whenever we remove, so we just show that when we can choose an element to remove such that when we remove this, then all chosen elements will still be non-adjacent. So then we can keep removing until there's nothing to remove, which is basically just induction. So anyways, once you make this observation, you're basically just finding a subsequence which is not adjacent of length which is 1/3 of the total length, and you want to find the maximum sum, which is just dynamic programming. So, and also, since this is a circular array, the first thing we do is we want to change this problem into a problem on a linear array. So the way we do that is we can consider the first element of the array, and there are 2 possible cases. The first case is if we choose the first element, then we have n divided by 3 minus 1 choices left for our other elements, and basically if we choose the first element, like 4 over here, then we can't choose this element or this element, so we can only choose elements within this range, which is described by this. So the beginning plus 2 and minus 1 from the end. But if we don't choose this, if we don't choose the first element, then we still have n divided by 3 choices, and since we don't choose this one, we can still choose anything here. So it's 1 from the beginning and all the way until the end. And then for the linear case, this is just a straightforward DP. So dp1 of I of j means we've processed the first I elements in the list A, and what's the maximum value we can get if we choose j of them and we did not choose the last element in the array, in the first I elements of the array. And dp2 is similar. dp2 of I of j means if we've processed the first I elements of the array and we've chosen j of them, and then the last one, and we also chose the last element of the first I elements. So the way the transitions work is if we didn't choose the last one, so if it's dp1, that means you didn't choose the last one, so that means you can choose the current one, which is, and so we add the value a of I, and then the state becomes dp2 of I plus 1 of j plus 1, because it's dp2 because we just chose the last element and we processed the new element and we added a new element to our sequence. But if we don't choose, then you can either use dp1 of I of j or dp2 of I of j, and then we basically just processed one new element, and it becomes dp of 1 because we did not choose the last element. And the answer is just the maximum of these 2. So let me check my ranking right now. I think it'll be interesting. Oh. I'm surprised that the last problem has so few solves. Anyway, second place is pretty good, but I missed it by 8 seconds, which, yeah, 8 seconds is a bit sad. But anyways, if you found this video helpful, then feel free to like and subscribe, and if you have any questions, then feel free to ask them in the comments below, so I'm able to help you.